I thought that was appropriate because what we've been trying to do in the research we've been working on is, I mean, that's pretty phenomenal, but we would like to actually make it better. So this is what we're doing. So we up? Okay. Yay! All right. So I'm Gary Mandel. I'm working for Out of Hand Displays, and I have an association with these groups who are working on the 6P color project. Come on. Come on. I think my clicker went to sleep. Okay, so come on. Okay, so this is a project that started off at Baylor University, managed by Dr. Corey Carbonara, and included a group of Dr. Michael Corpy, Dr. Brantley, who is over here, and is now CTO of 6P Color, Dr. Bogdanovich, if you are familiar with Kodak, Jim DeFilippis, and myself. So, this is a pretty nice picture. Pretty happy with it. This is, we're looking at an eclipse of the moon, and we're looking through the atmosphere. And this was taken by astronaut Susan when she was up on the space station. And we were talking to astronaut Susan about this, and she's really proud of this picture, and it's really pretty cool. But at the end of the conversation, she tells us, yeah, it looks really great, but that's not what it looks like. And the colors are not as vibrant, and there are gradients in there that don't show up. So we're kind of curious about what that is. And we start looking at what we're doing with her. So this is the gamut of the display we're using. And we show it to astronaut Susan. And we say, we need to find out where this color resides in here. So we hand her a spectroradiometer. She goes back up onto the space station, measures that color, and then comes back. And that's where the color lands. Well, of course it doesn't look right. It's out of gamut. We obviously, whatever we're doing here is not going to work for this picture to get this color. But not to worry. We've got the new XX 2020 Super Duper display made by the Super Duper Display Company. And it's got a wider gamut. And we can see that the color that we're looking for is within gamut. It's great. So we go to astronaut Susan. What do you think? Well, it looks a lot better. Much nicer. But, hello? As we're doing this, astronaut Bob pops in. Astronaut Bob was also on the space station when astronaut Susan took this picture. And he looks at it and goes, that's not what it looks like. It was much greener. And astronaut Susan takes an objection to this and says, no, it's bluer. And no, it's greener. And this goes on, gets into a pretty loud argument, eventually turns into a bar brawl. We have to call the cops, and it gets very awkward. So we want to think back. Why did this happen? And let's go all the way back to the beginning and start thinking about how do you see color? So this is a nice graphic of the vision system. And the biggest question is right now is, where do we actually see color? And where we actually determine color is not at our eye, but in the primary cortex, visual cortex. That's where that decision is made of what color we're looking at. So in a display, the way we're going to work with color is if we use a very wide distribution, as we're seeing on the top, we're going to have a more pastel color. That appears to us as more pastel. If we go with a very narrow spectrum, it shows a color with much more intensity. So obviously this takes us on to the next point of Wheel of Fortune. I'm sure everybody's interested in this. And we even have Vanna White here to help us with that. So this is our phrase. What does it say? So, okay, it's maybe not so easy to to read. Can anybody read this? Why? It's more data. You have more information you're working with, exactly. So let's go back to a display. This is a spectrum of a laser projector. I don't think it's this one, but it is an example. And if you look, we have these troughs down in here where there is no light. There's no energy output. And then we have these very narrow spikes that have quite a bit. This is what this is telling us, is it is giving us colors, but it doesn't have a lot of the information. If we go to something like this with broad spectrum, we have much more information to work with. And what happens is we end up with more metamers with the narrow spectrum than we do with the wide spectrum type of displays. So where we want to go with all of this is we still want to expand our sensation of color. We want to make that better. We want to increase our gamut. We want to have more information out to the viewer to disseminate more information to them. But to do this, what do we have to? We have to do some dealing with the spectral on that. We can't, going with a narrow spectrum may not be the best method. So the system we were working on, we call it the FCR system. Where this originally started is we want to get multi-primary data from the source to a display. And we're looking for a transport of some kind to do that. So on multi-primary, has it been done before? It's been done quite often, and this has been going on for quite a while. Universities have been building special displays. Genoa was an Israeli company that was going to go to market until they got bought by Samsung. And then way back, I think in the late 90s, Sharp came up with Quatron, which had a yellow primary. So it's been done before. Does anybody own one? No, I want to go out to Best Buy and get one right now, but I don't think so. Well, why? Well, we're going to have to make content for this because we want to light the primaries. Well, are we going to go through and build multi-primary standards? Probably not. How do we acquire an image? Are we going to have a 6 or a 12 multi-primary camera with multiple sensors? Probably not. Are we going to send individual integer information through the transport to drive this display? No. So are we going to build a proprietary system? No way. No one's going to do that. So what's our alternative? And that would be to just use the signal we have. And that just goes back to, well, what's the point? If I only have an RGB, then if I add more colors, all I'm doing is just making things up. So what are we going to do? So what we can't do is we can't change the current infrastructure. No one is going to build a new infrastructure to facilitate some type of multi-primary display. If we do build something, it's got to be backwards compatible. Not everybody is going to get rid of an RGB display in order to view this content. So our option is instead of redesigning everything, what we want to do is we want to look at the transport systems that are out there right now and then come up with a way just to interpret that data differently. So the way we would do this is move away from an RGB integer format to a colorimetric format. And this gets us in a couple nice advantages. So it hasn't been done before. Has anybody gone to the movies in the last 20 years? Because that's what you've watched, is the files in the digital cinema system are encoded as cap XYZ. They are not encoded as RGB. And that was because the DCI wanted to have a future where they didn't know what display technology was going to be out, so they still wanted that content authored in the past to be able to be displayed on whatever new technology came up. So it works, and in fact, it works very, very well. So if we're looking at XYZ, these would be the top values. So we have 0 to 1 and 3 axes. However, when we do this, there is a luminance component in each one of those. So our only option with these is to use 444 sampling. And it works for digital cinema because it's an enclosed system. The content that is authored for that is not going anywhere other than to a specific media block and used a specific way. So this isn't going to work for us. But there is YXY. So what we're doing is instead we use Y. We've been using Y on all kinds of things forever. But instead of doing it like an RGB, we're going to do a YXY. And that has a couple advantages. Y is Y. So those values don't change. XY are coordinates. They are not integers. So any changes in Y, cap Y, has no effect on little x, little y. So that also starts making things a little bit simpler. We start looking at processing is much more simple than if we do even with the current YCBCR system. So it works in 444 sampling, but it also works in 422 and 420 as well. So this is how we would get there. I apologize for the math. Really, all we're doing, we have to linearize. So if there's any kind of gamma or anything, we have to get rid of that. We're going to identify our RGB gamut. We're going to identify a white point. And we're going to build up this adaptation matrix. And that comes out with these values, SR, SG, SB, which are basically a combination, a centralization of our gamut. Then we put those in, we multiply those against the primaries. We put in RGB in one side, and we get cap XYZ on the outside. To get from XYZ to YXY is a simple ratio. So you can see in doing this, there's not a lot of processing. There's not a lot of headroom in order to get this done. And where that is an advantage is there's no latency in the processing. It's very fast. In fact, in most cases, you can have less than half a frame latency just in a prototype. So then the other thing we've been talking about is gamma. Well, why do we have an optical gamma going through the pipe? The best we can figure out is because we've always done it that way. Doesn't seem to be a real reason for that. So, and that all stems back when we were doing NTSC analog, and we had CRTs or image orthicons, then it made sense. But now in a digital world, we're not so sure. It doesn't really make that much sense to do that anymore. So instead of doing an optical nonlinearity, what if we put a nonlinearity into the stream that maximizes the data recovery? So if instead of doing a literal image through the pipe, what we want to do is we want to just take as much data as we can, pass it through there, recover it on the other side. So we call this DRR, or data rate reduction. And as it turns out, keep it simple. It's a power. All we're going to do is we're going to put a power on it. So we set a power value to encode, and we set the inverse to get it back. And since we are going to do this for data values, it makes things much easier. So we will have a power we will apply depending on the bit level and if it's an HDR or SDR image. So as you get to the other side of that, you're going to know that either with some type of metadata on the other end, and you know exactly what curve you're going to come up with. We can do another trick. On the top are a 12-bit, 10-bit, 8-bit YCBCR word that you would see in any type of data stream. Because X and Y are coordinates, if we modify that, all we're doing is we're changing our precision. We are not changing the color. So we're going to take the least significant bits and we're going to replace them with cap Y values. So I have a 12-bit stream. Really what I'm sending is a 16-bit luminance word and 10-bit coordinate, color coordinate. We can do that here with a 10-bit signal. Now I'm passing 12 bits. With an 8-bit signal, now I'm passing 10 bits. And these are our precisions. This is basically the variance you would get depending on the bit level where this changes. And you can see, even at 8-bit here, we're doing pretty good. It's pretty close. So this would be the encoder. Like we started off with, we have an RGB image. We linearize it. We're going to flag it for HDR, SDR. We're going to scale it. What we're going to do here is Y needs to be between 1 and 0. And that'll transform back on the decode side so that we can get almost anything out of that that we want. We convert it to cap XYZ. We bring it into cap to YXY, and we split it. We take Y, we'll apply our DRR to it. We'll take XY, and we're going to scale it. So if you look, this is 1931 on the end. If you actually look at the values, they don't go to 1. They go really to 7.74 and 0.84. So why encode beyond that? So what we're going to do is we're going to scale those down so that we're going to use every bit. Every integer in our coordinate is going to be a real value. It's going to be a color. We take that. Optionally, we could even apply DRR to little x, little y. We set our sampling structure. It goes out the pipe, and we have an FCR output. So this would be a DRR application. Nothing very special, except when we start it, we start with a 16-bit word on this. Hold that thought. So this would be a bit shift, not that big a deal. This is all very standard stuff. All we're going to do is once we set our subsampling, we'll shift things around to past the larger Y levels. And then we're going to stuff it into a data stream of some kind. So this is what it would look like with SMPTE 292. And if anybody's been around for a while, 292 goes all the way back to like the mid-90s when this thing was a standard. So there's no change. We're not going to change it. Even something this old, all we're going to do is in the slots where we have YCBCR, we're just going to substitute XS, Y, and YS into those slots. So it's not changing the signal. All we're doing is these represent a different value, a different parameter. Then for our payload ID, pretty simple. Bit 3, we would identify it as YXY. And then bit 2, over on byte 4, we can identify bit shift. There's 2110, not a big deal. This would be the cadence for a 444 signal. We would identify it in the SDP flag, and we would also put in a TSC flag that you're using a DRR transfer function. And it also fits in a 422 and a 420 stream. So we have cadences for those also. This is into 861. So we want to run FCR through HDMI or DisplayPort. Packs right in. No change at all. We're talking firmware. So how well does this work? It's great to talk about it, but does it really work? And one of the things we did, especially with DRR, is we had a lot of questions on, is this really the way to go? So we started off, we have 16-bit values. We normalize them to 0. We apply our tau value. We run it through the pipeline, invert it, bring it back, and then we'll do a subtraction with the original. So the top row of images are the first on the left is the 16-bit original, then a 12-bit pass, 10-bit pass, 8-bit pass. On the bottom is the subtraction from the original on 12-bit, 10-bit, and 8-bit. This is just a ramp, so this is pretty simple. But we can get into more complex images. And you can see here, this was an HDR image. And you can see that even in 8-bit, we're bringing back pretty much everything. We go to a more complicated. This one has a lot of clipping in the top. And you can start to see here in 10-bit, we got a couple of errors. And then it gets a little bit more in the 8-bit image. But we're still, if you do it by PSNR, and somebody just told me PSNR sucks. But you can look at it. You can see that, typically at home you're getting between 30 and 40, so, or 45. So we're doing pretty good there. Then we can take an extreme image, and you can see in 8-bit we still do have some errors, but our recovery is pretty good. And our recovery, we're actually bringing back 20 f-stops on this. So it's quite a bit of information. So we were pretty happy with the performance of DRR. So let's talk about the coding. We get all this stuff. We have it in the pipe. We've encoded it. We have our FCR pipe we're going to plug into our display. So we're going to plug it into an RGB display. This is how it would look. This would be the decoder in here, and then this would be the first part of the process in the display. And you can see by the yellow box, all we're going to do is a matrix to a standard gamut. So whatever the gamut is on that RGB display, we input a matrix, then we add, since it's linear, we're going to add our gamma back. Pick the gamma you want. It can be anything. What's the best for that display? And then it goes through the display process and onto the screen. This is a recovery from DRR. And we talked about when we were encoding, we had a 16-bit word. We end up with that 16-bit word. And what's key here is we end up with a 16-bit word regardless of the bit depth of the serial stream. So if we pass this through an 8-bit serial stream, at the display, we're still working with a 16-bit word. So now in the display, you've got plenty of data to work with. Now, at 8-bit, you saw there are some errors. It's not entirely correct. But you've got a lot more information, and you're not tied to the bit depth of the transport. This is the bit shift. It's just the unshuffle before we do the reconstruction from the subsampling. And this is the result, is by doing this and not doing an RGB encode, we have one format to feed everybody. If all of these displays have the FCR decoder in them, all of them are going to show the right color regardless of what the gamut is. So we don't care. That one could be P3, one could be 709, we could have a 2020. The phone could be some special gamut that somebody has. Since we're using a coordinate system, we're telling the display, I want this color, not that it's a combination of these three values. So finally, I'm sure everybody's going, when are we going to start talking about this? So let's talk about multi-primary. So right now, I'm feeding this HDMI. My guess is we're looking at 8 bits on the screen. So it's kind of a marketing term, but here it has more relevance, I think. We're looking at 16 million colors. So we have 16 million different gradients that we can deal with in the image. And you remember, one of the things that astronaut Susan was talking about is she couldn't see that gradient that was actually in this picture when they were looking at it outside of the space station. There's been a lot of work now. We're seeing displays now with 10-bit, which is great. Now we got 1 billion colors out of something like that. If we were to take an 8-bit display and just add one primary to it, we have 4 times the colors that we do with a 3-color 10-bit display. If we did it in 10-bit, we're at 1 trillion colors. We have 1 trillion different levels to work with 4 primaries. If we did 6 colors at 10-bit, we're at 1.15 quintillion colors, so at 10 to the 18th. That's how many different levels we would have coming out of that display. To put it in context, the number of stars in our galaxy is 10 to the 12th. So we're talking about a lot of different ways of displaying color. What do we have to do with acquisition? Do we need a special camera to work with this? No, we don't need anything special. If you look at the gamuts from the cameras that are out there now, there's plenty large. There's plenty of volume there in order to work in a multi-primary display. So in essence, we don't have to do anything here. So we talked about in an RGB world, here's our decoder, and the yellow box is where we actually go out to the gamut of the display. So what's going to change in this process to do a multi-primary display? That box. It's the only thing that changes. So instead of doing a matrix to 3 primaries, we are going to do a set of matrices to multiple primaries. But it really, since we start with a XYZ data, we can go anywhere with this. So our distribution, how are we going to do it? One of the big questions is, all right, so I got all these primaries. How do I distribute my data to these so that they actually works and I make use of them? So we're going to take XYZ data and we're going to distribute it to each one of the primaries. One of the limitations we have to work with is we have to use an identity matrix. It can't be a non-square matrix. So one way we can do this we call pseudo-white. And we're actually going to say white is a color primary in our design. And we'll break up our gamut into kind of pie-shaped sections and distribute to 2 of those colors and to white. The second method is layered triads, where we're going to have a set of triads to distribute, and we are going to do a set of layers of 3 primaries, driving 3 primaries in each layer. So this is pseudo-white. So what we do is we have white. Now white actually is a primary in this. We have our XYZ values that we bring into it. We set our position within that volume, and that's our color. So we will distribute. So in this example, we would distribute to red and yellow and to white in order to drive the color that we wanted to see. Now, this is how it would break up. We would have matrices for each one of these pie shapes. Where this kind of gets more difficult is we're using white, and white is a total distribution. White's going to go to every primary. So that gets a little bit complicated, and that starts getting our processing headroom starts getting a little harder to control. So this one isn't, while it works, it isn't the preferred method. What we have done, what we're using now in our stuff, is layered triad. So we're going to calculate the number of possible triads within those primaries. We are going to scale down those triads to the minimum number we can use. We want as few as we can get. We'll define the position of the triads. We'll develop matrices for each one. And then we're going to do a set of values. We're going to derive these values through an inverse matrix and then look for negative values. So here's a sample gamut of what we're doing. This is 6 primaries. This is where those primaries would be located. So within 6 primaries, we have 20 possible triads that we can put in this. But many of them are redundant. And in fact, 12 of them are completely redundant. We can just toss these. These don't help us. Now, we don't have to choose exactly those numbers. All we have to do is make sure when we get to our final count that they're all exclusive. So we have 2 primary triads where the majority of data is going to land. And then we have an ancillary group of triads. What we're going to do is we're going to map out where those positions are, and those are the values we're going to use for the 8 triads. This is how the 8 triads would look. We would set up matrices for each one of these, and these would handle the distribution if our value lands within that triad. So in this example, we're in a 6-color gamut. We're always going to have 2 triad levels. So what will happen is the color is going to land in both. So you can see on the top we have an RGB triad that it lands in, and then a green, cyan, yellow triad that it lands in. So we have to make an adjustment on this. We're going to drive all 6 primaries, but luminance is going to be double because we're doing XYZ cubed. So we're going to divide by 2, and we're going to drop our luminance down to correct it. So now we can start getting into some interesting thoughts. Normally when you're thinking of multi-primary, you're thinking about this. We could have a 4-primary display. We could have a 12-primary display if you wanted. With layered with both distribution systems, it doesn't matter. And actually, if you take this down the road, we start getting to the point, what does it matter to have a gamut standard? Because we can drive anything we want. So this opens it up. Since I'm using a coordinate to say this is what the color is. So I don't care where these primaries are as long as I develop the display to read the data correctly and replicate that color. So we can do some other things. This is a 6-primary display too, but we have 3 whites, and they're all very wide, have a very wide energy distribution. So we have 3 primaries that are very narrow, and we have 3 whites to fill things in. Or we could have dual gamuts. Here we have a very narrow gamut driving an RGB, very wide RGB color set. And then we have a very wide band, lower gamut, smaller gamut to drive it. And these would center the same. They would have the same center frequency. But this would now, you can see we have some crossover that would stop some of this metamer problem. And this gets very weird. So I don't know if anybody's heard of melanopsin, of what this is. This is really some cool stuff. So in your retina, normally when we talk about vision, we're talking about the rods and the cones. So in this, we always think of that is the energy that we are absorbing to develop our sensation. Well, we also have these things, the IPRGCs. And these are these are a set of ganglion cells that are closer to the light source. So light actually is coming from this direction into the retina. And these secrete a different enzyme. And this enzyme isn't in our vision system. This enzyme changes other things, like our clock, our circadian clock. It has effects on our sleep and our mood and our activity. So now this brings up another thought. What if we had a display that output, this is in about the 490, 492 nanometer range, when this starts reacting. So I get on a plane, I have my display that takes advantage of this. I land at my destination, and I don't have jet lag. You could do that. That's going away, but that's a ways off, but that is something certainly possible if we can generate light in that spectrum. So we have TVs. So I would like to make them multi-primary. Well, what does that take? If I've got an 8K TV, which don't seem to be doing very well right at the moment, I can make it a 4K 6-primary display. And it's, what are we doing? We're changing the filter and we're changing some code. That's all we have to do. Now we have 1.15 quintillion colors. And how much does that cost us? Really, almost nothing. So this is a system we have at Baylor for our testing. We have an RGB projector, a cyan, and emerald, which is a green, which is a little higher frequency than what the green is in the RGB projector, and yellow. So we've worked with Simulate Scratch, and they've built us a special version that outputs an FCR image, and it just plugs right into an Object Kona 5. We take HDSDI out to these LUT boxes, and the LUT boxes convert to the projectors. And we have 6 color primaries. All we're doing in the projectors that are not RGB is we've taken the spinning wheels out, because these were sequential color, and replace them with a set of fixed filters. And now we're down to 1 color. This is the gamut that comes out of this. So these are institutional projectors, and we got them used. So the cost was nothing. But out of these 4 projectors, this is the spectrum we're getting out of it. and it's pretty broad. And it also is very wide gamut. We've built a video wall. What we did is we added a cyan chip to it. And this is down in LA right now. And we're showing 4-color primary images using an FCR system. Basically, it's the same thing. We're working out a resolve into a deck link card, into 2 LET boxes. One feeds the wall as RGB, one feeds the cyan color. So pretty much what we got is we can develop content and media that displays on anything. We don't have to worry now. We're not worried about the gamut. We're not worried about the white point. And we're not worried about the gamma, because we can deal with all those at the display. All color possibilities are presented. So we're not limiting anything. The display sees everything. Gamma isn't an issue because we're not going to put a gamma into the image. We're going to send it down with a DRR nonlinearity, and you're going to be able to decode that however you want. You end up with a linear code word at the display, and now you just take whatever gamma you want to use. And again, we're doing this in a single channel. We're not doing it in 3 channels like we have to do now. We just change Y. And because we're using little x, little y, any change in cap Y has no effect on our chroma or our hue. And our feeling is this opens up technology, opens up to new technologies in display. We can increase the display market, and more companies can monetize what they're doing. So that's about it. Questions? John?
Yeah. So Gary, what's the experience? Like, okay, so you have the projection system at Baylor, and in LA you have an LED wall that you've done this. I mean, with HDR, there's a real difference that people see, and it's like, oh my God, I thought that was 4K. Oh, it's better than 4K, you know, because there's a lot of color, and there's both the wide color gamut, and there's the high dynamic range, and so on. So it looks good. It's almost like 3D out of a TV, right? But what about here? What's the experience looking at? I mean, you've probably seen these things.
Yeah. What we're doing here, of what HDR did to luminance, we're doing with color. So we're enabling displays with much wider gamuts than we can do now with this type of encoding. So you're going to start seeing colors you are not seeing now. And we've demonstrated this. We have been working with NASA on some of this. And we've had some of the astronauts in. And they've seen a distinct difference. They're saying that what they see in the 6 primary is far closer to what they're seeing out in space than what we're seeing now. And we're using space as an example because that's an extreme. You don't have an atmosphere or anything to destroy what colors are available to you, and there's much more energy out there to do it. But when we bring it down here, it's going to be the same thing. Is there are colors here that we can't do, and if we want to take it a step further, like with the melanopsin idea, what other things can we add? Can we extract, or can we communicate different emotions more than what we're doing now?
Is the demo is the LA open to the public? Is there a way that people can see?
We can set something up. Right now, it's just being used for research. But if you wanted to see it, yeah.
Can you say where it is?
It's over at Tiffin in Burbank.